Hi guys, and welcome to today's video. In today's video, we're gonna see stack in embedded system programming. We'll start first of all by describing the necessary tools to be used to set up our STM32 based project. Then we'll start tackling the stack topic by speaking up about the generic definition of stack in programming. Then we'll go to define and get to know how stack is used, especially in embedded system programming. Within the context of embedded systems programming, we'll see how we can allocate stack using the Linka script. Then we're gonna see, as part of our STM32 based project, how the stack is working on an ARM Cortex-M microprocessor. So we will use the STM32 project to demonstrate how the stack is being used and working in an ARM Cortex-M based CPU. Finally, and as a key feature of the stack memory usage in embedded system programming, we'll see how the stack is playing a critical role on interrupts and exceptions context switching. Now, for our STM32 based project, we'll need a hardware to be able to load the project and debug it. The requirements in terms of hardware will be the STM32 L4 Nucleo port. Nevertheless, as the memory layout across the different STM32 microcontrollers is quite similar, then you can utilize to run the project any kind of similar STM32 port. The only condition is that it should have a Cortex-M3 or a Cortex-M4 microprocessor. In terms of toolings, all the tools are located within Wadix Technology tools directory. This is the link to the GitHub repository for our tools. Finally, the project source code will be located in this GitHub repository. The different slides and links will be provided as part of the YouTube video description. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now, in terms of tooling, our Wadix tools GitHub repository offer quite big number in terms of toolings and applications. Nevertheless, for our Makefile based project, we will need mainly the ARM GCC compiler. This is the ARM non-EOB GCC compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our Makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU Make Build tool. And finally, we'll need set of tools and applications to be used in combination with our Makefile. So those applications will be used as part of our Makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Swicthing does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Swicthing applications as well as make build tool as well as the ARM GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now if we inspect again, as you can see, the previously added tools has been removed. Now I will just execute again this install PowerShell to be able to move forward within our Makefile based project. As you can see, this has been added again. Now we can move forward and check out our Makefile based project. Now, as you can see, this is our STM32 based project. This project is a Makefile based project. So all the rules to build the different C files and generate the object files as well as the final ELF binary to be loaded into our microcontroller will be embedded within this Makefile. Now the examples to be compiled, which will show us how the stack is working on an ARM Cortex-M based microprocessor, will be located under this directory, as you can see. The instructions to build this project will be located in this README file. The stack is a generic concept within different programming languages. And in terms of a generic definition, the stack is just a data structure that is used to hold different data elements. The stack will support two main operations, push and pop. The push operation is used to store elements within the stack data structure. The pop operation will be used to get the different data element out of the stack data structure. In terms of structure, the stack will follow the LIFO data structure, means last in, first out. So the last element that has been pushed into the stack will be the first element to be taken out using the pop operation. Here, for example, the last element that has been pushed in the previous operation was this one, 3. If we execute a pop operation after this push, then the first element to be taken out will be the last one that has been saved. The stack will keep track always of the most recent element. So the last element that has been pushed to the stack, this is the element that always the top of the stack will be pointing to. The stack as a data structure does not support random access. Hence, we cannot get a data element within the middle of the stack. This is not possible. We can just get the element via pop operation and will be always the top element within our stack. The rest of the elements cannot be accessed. The stack is quite powerful in terms of usage, and you can see it used within function calls, recursion, undo mechanism, expression evaluation, as well as interrupts and exceptions context switching. The stack, as stated before, will follow the LIFO concept, or the last in, first out. This is the exact opposite from the FIFO concept, which is first in, first out. This means that the last element that has been pushed to the stack will be the first one to be taken out once we execute the pop operation. So always the stack will be pointing to the last element that has been pushed. Hence, any pop operation will be executed will take out the last element that has been pushed. If we try to project the definition of the stack data structure on embedded systems programming, we're gonna see that the stack will be implemented and allocated a dedicated memory region within our device for the data structure to embed and store the different data elements. Hence, the stack is no more a generic data structure. No, it will be data structure that will be allocated a dedicated memory region to store the different data elements. The allocation can be done at compile time by specifying the base address and the end address of the memory region to be allocated to our stack. Or we can update the stack pointer to point to different memory region at runtime. The stack pointer, this is basically the CPU register used to point to the last element that has been pushed to the stack. And hence, it is quite critical to initialize the CPU register to the top of the memory region that is allocated to our stack. Now, in terms of topologies and architectures, the stack on embedded system programming can be upward growing or downward growing. This means if it is upward growing, then the top of the stack or the CPU stack pointer will increment after each pushing of new element. And this will be the direction of our stack pointer. More we push elements, more the stack pointer will increment to keep up with the idea of having the stack pointer pointing to the top of the stack. If the CPU architecture is implementing the downward growing stack concept, then the CPU stack pointer will decrement after the push of each new element. Again, this is needed to have the stack pointer pointing always to the last element that has been put to this stack area. So, more we push elements here, more the stack pointer will decrement to keep up with the idea of having the top of the stack pointing to the last element that has been pushed. Now, the location of the stack may vary from one system to another, and also may vary from the user configuration. Means there are systems that they enforce the stack to be located on a fixed memory address. Hence, we cannot update the location of the stack area. However, there are another set of systems that allow the stack to be located in different memory regions. Hence, the user can allocate the stack area in this memory or this or this. It is just a matter of programming the start address of the stack, and this will be done by updating the stack pointer of the CPU. from low-level embedded system programming point of view, the program or the binary will consist of set of memory segments needed to maintain a proper execution flow of our program. In terms of sections and memory segments, we'll have a dedicated segment for our code, and the code here will consist of set of instructions to be fetched and executed by our main CPU or processor. This code segment may contain as well any kind of const data, and const data is the data that is marked with the const data type qualifier. We'll have as well another memory segment to be allocated for the different static and global variables needed by our program. Then we'll have another section and memory segment to be allocated for the heap. And the heap is used mainly to allow the dynamic allocation for the different structures and variables. And finally, for our stack area, we'll have as well a dedicated memory segment to hold the different local variables within the context of function call, as well as holding the different input parameters for a function call. And finally, it can hold as well the different CPU state registers that will be saved and restored during an interrupt or exception context switching. Within the context of embedded system programming, the linker script is the translation layer between the hardware representation of the different memory regions supported by our device and the software representation needed by our program to allocate the different sections and memory segments to those memory regions. In another word, the linker script is the place where we are going to initialize and allocate the different sections and memory segments to the supported hardware memory regions. Now, this is an example of GCC style of a linker script. And as you can see, we will need first of all to define the different memory regions supported by our system, like the base address and the size of each of those memory regions. Then we will need to allocate the different memory segments that we have seen in the previous slide to the corresponding memory region. Hence, the content of those sections and memory segments will go into those memory regions. Now, for our stack area, we will need to specify the initial value of our top of the stack. In most of the modern systems and microcontrollers architectures, the stack area will not have a fixed address range. Actually, we can assign to our stack area any memory region that allow read and write access within our system. This gives a lot of flexibility to our program. Therefore, and to properly assign the initial value of the stack area, we will need within the context of our linker script to specify the top of the stack area from where our CPU will start pushing and decrementing basically the stack pointer. So this value will go to the CPU stack pointer, and then once the CPU start executing our program, every time we'll have a push operation, the stack pointer will decrement by the size of the pushed data element. This is of course if our stack pointer is decreasing. And by the way, this direction of our stack pointer is supported by most of the modern processor architectures like the Cortex-M and RISC-V. So here, each time we push a new element, the stack pointer will be decrementing by the size of that element. And if we are going to pop that element, then the stack will increment by the size of that element that has been popped up. Here, as you can see, we have initialized the symbol stack top with the memory region or the top of the memory region that will be allocated to our stack area. So it can be this one or this one if the user would provide this as input to our linking stage. The stack memory area within an ARM Cortex-M based microprocessor will not have a fixed address range. Hence, we'll have basically the freedom to allocate any memory region to our stack area. To enable this kind of flexibility, ARM has exposed to the user what is called the stack pointer register. This is the stack pointer or R13 register. This one will be pointing to the top of the stack memory region. If we push one data element to the stack, then this stack pointer will decrement by the size of the data type that has been pushed in. If we pop up one element out of the stack, then the stack pointer will increment by the data type size that has been popped up. The stack within an ARM Cortex-M microprocessor is fully descending stack. Means if we push an element, then the stack pointer will decrement as stated with the size of that data element that has been pushed in. The important thing is that the stack pointer must always point to the last used location, or to be more accurate, to the last data element that has been pushed to our stack. In Cortex-M microprocessor, we will have the support of two stack pointers. Those two stack pointers are banked. Means will not use those two stack pointers in the same time. So either we'll use this or this. This means that this generic stack pointer CPU register will be using the value from this process stack pointer or from this main stack pointer. This depends, of course, from your configurations and settings. The main stack pointer, this is to be used for your main program. However, the process stack pointer, on the other hand, will be used in general for the different threads and real-time operating system based tasks. In general, the main stack pointer will be used as a main CPU stack pointer after reset or during the boot up of your main program. However, if we're gonna run a multi-threaded based operating system, then the main stack pointer will be mainly used for interrupts and exceptions. And for the different threads and tasks, we'll have basically the process stack pointer to be used. The stack area will be used as well to back up and restore the different CPU registers during exceptions and interrupts entry and exit routine. Now the linker script, which will be used to represent the hardware memory layout of our system and expose it to the software, will be located within our project under this directory. This is actually the source of informations for our embedded project about which memory regions to be used and which memory segments to be allocated within those memory regions. So here, as you can see, I have created a representation about the hardware memory regions supported by our microcontroller system. And as you can see, I will have two main regions, the flash memory region, where I am going to put the code and the const data. Then I will have this volatile RAM region, where I am going to put the different global and static variables. And here, of course, I will create different sections to allocate the different memory segments within those memory regions. Here, for instance, I am putting the ISR vector table within the flash memory. Here I am allocating the text, which is our code memory segment, as well as the read-only data and the const data within the flash memory. Now for the stack memory region or area, and this is basically the heart of the interest of this linker script within the scope of this video, I will need to expose and export this symbol vStackTop to indicate to my embedded software the top of the stack memory area. And hence, I will be able to initialize properly the CPU stack pointer with this value of this top of the stack. Now the value here, it depends if it is user specified value or predefined one coming from this linker script. Now here I didn't provide any user-based stack assignment or allocation, hence we'll fall back to the default value. And here the default value specified by this linker script will be the top of our RAM memory region. So it will be 20,004,000. And this one should be then used to initialize our processor stack pointer. Now, once we exported this symbol via this provide GCC style based linker script API, we'll be able to import it within our startup code. So here, this is our startup code. Now, on ARM Cortex-M based microprocessor, the first values to be assigned to our program counter and stack pointer will be taken out of the vector table. So, after power on reset, the processor will try to fetch the vector table to locate the initial value of the stack and the initial value to be allocated to our program counter. So the first two elements of our interrupt and exception vector table will be the top of the stack and the first instructions, let's say, or address to be fetched and initialized to our program counter. So the first element, as you can see, in the top of the stack. Here I will put the address of our reset handler or reset ISR, and hence the first function to jump to will be the reset ISR, and the first instructions to be executed will be the instructions located within our reset ISR function. Now, as you can see, the top of the stack, which will be the first element of our vector table, is just a symbol that has been imported from our linker script, as you can see. With that way, we'll be able to create this link between the hardware layout and the software layout. So everything will go through this linker script. The first example here will show us basically how the stack is operating on an ARM Cortex-M microprocessor, and we'll see how the push and pop operations will alter the value of the stack pointer. Now we'll try to compile this project. So the instructions to compile and build this project will be located in this README file. Let's clean up the project initially. Then rebuild it. Done. Now we'll have a predefined Keil project to be used to load and debug the software running on our STM32 microcontroller. We'll load the binary into the flash memory. We start a debug session, and here we go. We will jump into our example. Now we'll try to focus into the assembly part of our code. Now here we are within the first instruction of our example. And as you can see, we'll have this push instruction or operation to be executed. In general, for different function calls, we'll have the first and last operations within the scope of the function. Stack-based operations means push, then later pop operations. We are trying here to preserve the value of set of registers that gonna be modified within the scope of the function. Hence, we are doing kind of backup of the values of those registers within our stack. And then later on, once we are trying to return out of this function, we'll need to pop up those saved registers. So this is one of the main use cases of stack area. Will be used to backup and restore the content of the different CPU registers to be used within the scope of a function. Now, this is the value right now of our stack pointer the moment we are jumped to this function. Now, the stack pointer here, once we execute this push operation, will decrement because the stack within an ARM Cortex-M is moving down. This is the topology used on ARM Cortex-M, and it will decrement by the number of the data elements to be pushed into the stack times the size of those elements. In our case, the different registers within an ARM Cortex-M are 32 bits registers. If we'll push 2 registers into the stack, then the stack pointer will decrement by 8 bytes. Here I have created some basic function. Then I invoked this function within this example. Now let's move on. So, as you can see, we are here in our add function, and again, the first operation to be executed will be a push operation. This is needed to preserve the values of the different registers once we want to jump out of the function and return to our main program. So this is the value here of the stack pointer, and if we execute a push operation, then this value must decrement by the size of our register. Hence, it must decrement by 4 bytes. And here we go. So the value of the stack pointer has decremented by 4 bytes. Then we continue the execution of our function, and on the bottom of the function we'll have this pop operation. This is again another stack based instruction, and use it to pop up the data element out of the stack area. So here we're gonna restore back the initial content of our R7 register. So as you can see, we'll have this duality between push and pop operation. We push in the beginning of the function, then we pop at the bottom of the function. It's like a backup and restore mechanism. If we do a pop operation, then the stack pointer will increment by the size of the data element to be taken out of the stack. The size of the register is 4 bytes, So the stack pointer will increment by 4 bytes, as you can see, and the R7 register will be restored with its initial value. We'll try here to highlight the impact of the push and pop operations on the stack memory region itself, and we'll see especially that the CPU stack pointer will be always pointing to the last element that has been pushed to the stack. So we load our binary into flash memory. Then we start a debug session on the binary that has been loaded into our STM32 microcontroller. Let's jump into our function. Now here, the value of the stack pointer is this 20 million 3FD8. So we copy over this value, then we try to inspect the content of this address using the Keil memory region. Now, this is the top of our stack. If we're gonna do a push operation, then the stack pointer will decrement by the size of the element that we are saving. This is the 32 bits register, so the stack pointer will decrement by 4 bytes. This means that the expected value of the stack pointer after pushing the content of R7 register will be D4 instead of D8. This is the content of our R7 register, and this is the content of this 20 million and 3FD4 address. Now, if we do a push operation, then as you can see, the content of R7 register has been pushed into the stack. So the stack pointer has been decremented by 4 bytes, and the content of R7 register has been moved to the stack memory area. And as you can see, the stack pointer will be always pointing to the last element that has been pushed into the stack. This is a top-level view of the flow used during an interrupt, an exception, context switching routine within an ARM Cortex-M based microprocessor. The important thing to write it down out of this flow is that the stack area will be needed to back up and restore the CPU state during an interrupt or exception context switching. If we'll get an interrupt or exception, then the hardware will do a partial backup of different processor registers, and this backup will be within the current active stack area. So it can be the main stack pointer or the process stack pointer. So after doing this partial saving, then the current active stack pointed either by the main stack pointer or process stack pointer will looks like this. So registers R0 to R3, R12, link register, program counter and XPSR register will be pushed into the current active stack area. And of course, the stack pointer will decrement and will be pointing to the last element that has been pushed into the stack. In our case, will be the R0 register. Then of course, after we jump to our interrupt and exception handler, and depending of course if we have been executing using the process or the main stack pointer, then the hardware may switch or not the stack pointer in use. Interrupts and exceptions handler will always use the main stack pointer, and hence if the program before jumping to the exception and interrupt has been using as well the main stack pointer, then nothing will happen and will keep using the main stack pointer area. However, if the program has been using the process stack pointer, then of course the hardware will switch to use the main stack pointer. And later, during an interrupt or exception exit, then the hardware will need to restore the CPU state. This is done by popping up the different CPU registers that has been previously pushed to the stack area. Anyhow, what we need to keep in mind is that on an ARM Cortex-M microprocessor, we should have always two stack areas, one allocated and pointed by the process stack pointer, and the second one will be pointed by the main stack pointer. And based on the use case and the need, we may have both stack areas used, or we can just utilize the main stack pointer. So this is our second example, and in this second example we'll try to trigger an interrupt within the ARM Cortex-M microprocessor. The idea behind this example is to show up how the hardware will push and save some of the CPU registers into the current active stack area. The interrupt to be triggered will be the Cortex-M SysTick timer interrupt. Therefore, we had to configure our timer to generate this interrupt. And once we get this SysTick timer interrupt, we should end up in the SysTick timer handler. Now let's try to build our project. Done. So we'll load the binary into our microcontroller. Then we start a debug session. We go slowly. We'll try first of all to set a breakpoint into the instruction or the code line to be used basically to enable the SysTick timer. Then we'll set up another breakpoint in the first instruction to be executed by the SysTick handler. So right here. So we should not execute this push instruction. The idea is to observe the impact of the interrupt context switching on the stack pointer and the stack memory area. So this is the initial value of our stack pointer. Once we get an interrupt, the CPU or the hardware should save some of the CPU registers into the current active stack area. On Cortex-M, we'll have two sets of stack pointers. We'll have the main stack pointer and the process stack pointer. By default, and after power on reset, the default stack pointer and stack area to be used will be always the main stack pointer. Therefore, the CPU stack pointer register will be always pointing to the main stack pointer. And hence, during the interrupt context switching, in our case, the CPU registers will be pushed to this active main stack pointer memory area. So once we get the interrupt, we will see that the stack pointer will be decremented by the number of the CPU registers that has been saved times the size of each of those registers. In our case, all registers in Cortex-M are 32 bits or 4 bytes. Nevertheless, there is one important note, is that on Cortex-M, and to be more precise, in Cortex-M4 as well as M7, the processor will try to preserve 8 bytes alignment for the stack. So the stack pointer, after we get basically this interrupt context switching, the processor will force it to be 8 bytes alignment. And if it is not the case, so beside the CPU registers to be saved, it may append certain bytes to preserve this 8 bytes alignment. So in our case, the CPU in general will push to the stack during an interrupt context switching R0 to R3 register, then then R12 register, then link register, then program counter, then XPS register. So 4, 5, 6, 7, 8. So in total, we'll have 8 registers. Those will be the equivalent of 32 bytes. However, the stack pointer may not get decremented only by 32 bytes. If the final value of the stack pointer after getting decremented is not 8 bytes aligned, then the CPU may push a set of dummy bytes into the stack memory to preserve the 8 bytes alignment. Eight bytes means the address should be 0 or 8. So the first digits should be 0s or 8s. So this is how the address should end up. Now let's see what we have here as initial value for our stack pointer. So this is DC. Now, if we subtract 32 bytes from this DC, so DC minus 20, so the 32 bytes in hexadecimal are 0x20, then the end result will be BC. BC is not 8 bytes aligned. The nearest here 8 bytes aligned, because our stack is decrementing, will be B8. Hence, In our case, the address of our stack pointer after the context switching should end up by B8. So the CPU will save those registers, plus it will add dummy zeros, so 4 bytes zeros, to enforce this 8 bytes aligned. So this is not 8 bytes aligned. So let's see what will happen. We run, and here we go. So the stack pointer has been updated to this value. So it gets decremented by 32 bytes. This is matching basically the CPU registers that has been saved, plus extra 4 bytes to preserve basically the stack 8 bytes alignment. If we try to observe the content of this memory area, we can see that those CPU registers went actually to the stack. So the top of the stack will be the last element that has been pushed into the stack, which will be our R0 register. So this is R0, this is R1, then this is R2, and so on. However, instead of having only 32 bytes, as stated, we'll have extra 4 bytes to preserve alignment. So this in general should be the XPSR register value. So this is the first register to be pushed during a context switching. Nevertheless, beside this XPSR register, we see this extra 4 zeros. So instead of pushing as first element the XPSR register, the hardware has decided first of all to push those extra 4 zeros, then starting to push the different CPU registers. With this extra 4 bytes, we'll be able to have 8 bytes aligned stack pointer.